Well, thank you all for virtually coming out here today. I'm excited to meet you and sorry that I can't meet you more in person. So I want this to be as interactive as possible. So please go ahead and stop me at any point that you have questions. And if anything is confusing or if you just like to spend another minute on a topic, just say so and we can see where we go. So what I'd like to talk to you about today is noise in lattice QCD calculations, but really more broadly than that, noise in quantum Monte Carlo calculations. Because everything that I'm going to tell you today applies to lattice QCD calculations, but it applies anywhere that you're sampling from a path integral in order to simulate quantum fluctuations. So this could be the one-dimensional simple harmonic oscillator just as much as lattice QCD. And more specifically, I'm thinking about any setting where you have some observable O and you want to calculate its expectation values, which are path integrals, where you have some field U, you have some path integral weight, e to the minus s, and then you integrate over all fields in your configuration space, evaluating your operator in each field configuration. And that's the path integral definition of an expectation value. With perhaps, depending on how we normalize things, some z inverse out front from the partition function. And by Monte Carlo simulations, what I mean is what you're all at this point pretty familiar with, which is that we approximate these integrals by an ensemble of n random field configurations, and we calculate our observable in each of these configurations. The trick is that the probability distribution for each of these UIs needs to be taken to be e to the minus s. And if this is true, then by the central limit theorem, you will get the right answer up to corrections suppressed by 1 over root n from your statistical noise in the infinite statistics limit, n goes to infinity. So is everyone happy with this definition of what we mean by Monte Carlo and path integrals and sort of getting notation set?
I was gonna say, are you able to see the chat?
No, I can't.
Okay, yeah. So there's a chat feature. So because I saw a few, and I didn't want you to think that no one was responding.
Very good. Okay, so what's the best way to do this? Should I pull up the chat on another screen here so I can see that?
Sure, maybe. If you can get that figured out, say otherwise, just every now and again check. Or otherwise, I can let you know when there's been a question.
Yeah, actually, if you don't mind, just letting me know when
Sure, I can do that.
things pop up, or to folks, feel free to be vocal because I can hear that right away. Okay, so the last thing on here that I'd like to point out before moving on is the importance of this e to the minus s factor. And in particular, if we were really just starting out with good old quantum mechanics, we would set up e to the is as our path integral weight. However, this does not work for Monte Carlo because of the notorious sign problem, which is e to the is cannot be interpreted as a probability distribution because it's a complex number. It's not something that can be normalized and interpreted as a probability. And so you can't sample from e to the is as a probability distribution, and this Monte Carlo strategy doesn't even get off the ground. So all the calculations that we do with standard methods in Lattice QCD are restricted to Euclidean spacetime where the action is e to the minus s. And similar things hold true for nuclear many-body theories, chiral effective field theories with Green's function Monte Carlo evaluation, the many other places where quantum Monte Carlo techniques are used to evaluate path integrals. So, to again just make sure we're all on the same page, at this point we should have talked about in this school some hadron correlation functions, I'm sure. So let's think about a pion correlation function and the statistical noise that it's going to have. So I'll define my pion correlator as G for Green's function. Sub pi of t is some correlation function that involves some pion with momentum p. I'll set to 0 for now, annihilated at some time t, and a pion creation operator placed at some time 0. And should have turned off notifications, I see. What we usually do is evaluate this using our path integral definition. So Lattice QCD can have the action split up into a gauge field action that doesn't depend on the fermions at all. I'm presuming you've all seen the Wilson gauge action at least once sometime this week, but at this point it can be schematic. The quark action, we know, is always just d slash plus m, where all of the interactions are the fact that d slash is some matrix that depends on the particular gauge field. And then we need some pion interpolating operator. Let me choose some pseudo-scalar pi plus operator. And then we know that since our quark action is just free fermions in a background gauge field, we can evaluate the fermion part of the path integral exactly and just use Wick's theorem to perform the contractions, which there will be one or two of, depending on the flavor content, just one in this case without pluses, and get a determinant, let's say squared if we just have up and down quarks, and then when the dust settles from the Wick contractions, we'll just have the trace of d slash plus m inverse squared. So the matrix norm of the propagator. And then Monte Carlo calculations of Lattice QCD proceed by calling this e to the minus gauge action times the determinant squared the effective Boltzmann factor that one samples gauge fields from. And then this just becomes some Monte Carlo evaluation of n gauge fields where we evaluate propagator on all of them. And the point, once we are holding the pion correlation function, is that we can also write it as some thermal, or for simplicity, vacuum to vacuum, neglecting thermal effects matrix element. And you've already seen the spectral representation, I know, from Christopher Robin's fitting lectures, if not before. So we can insert a complete set of states and switch from a pion field at t to a pion field at 0 with explicit time evolution factors. And get that our correlation function should be some sum of exponentials. And so if we're holding the correlation function in our hand, we can pick off the pion mass, the leading exponent here, by just taking a log derivative of the pion correlation function. And this is our effective mass plot that I'm sure you've seen plenty of already this week. Here is one example of some pion effective mass plots. And the bottom red points here show the effective mass for a zero momentum pion at rest. And what you can see is that as you go to very large t, then this asymptotes towards a constant, and that you can read off as the pion mass, which was a very heavy 1.2 GeV in this calculation. And then the other colored lines show the effective masses for pions with 2, 3, and 4 units of momentum. And the mass goes up in agreement with the square root m squared plus p squared dispersion relation. But what you should also notice is that for the red points, the error bars shown on the effective mass are constant independent of time, whereas for the other colors showing boosted pions, the error bars start to increase as time is increased, and in fact, they increase roughly exponentially. And this is the generic behavior of hadrons in lattice field theory or any states in quantum Monte Carlo, really. So if we look now not at pions, but at nucleons, then we could look at nucleons and nuclei using exactly the same set of techniques. And if we look at the effective masses for a proton, deuteron, helium-3, helium-4, so baryon number 1, 2, 3, 4 systems, then should notice that all of the states here look much like the boosted pions shown on the right, where you have this exponential degradation in the signal to noise, the explosion of these error bars as time is increased. And that degradation increases much more rapidly as we look at larger baryon number systems. So this is one of the main obstacles facing lattice QCD calculations of nuclear physics, that the statistical ensembles you need, at least naively, are exponentially large in the baryon number, though in some intermediate regions of time, that's not always the case. And the same applies to calculations of heavily boosted systems, which are becoming increasingly interesting these days as ways to probe late cone structure. Things like parton distribution functions can be accessed by looking at highly boosted systems in lattice QCD calculations. And again, the interesting limit of large momentum faces an exponentially hard signal to noise problem. So with that preliminary out of the way, that signal to noise behavior is what I would like to turn to next. So does anyone have any questions at this point? Okay, and have you all been seeing effective mass plots, things like this week? Is this all stuff that feels like stuff you've seen before?
Yes.
Yes.
Good.
I
Okay.
had one quick question. Back one page.
Yeah.
Oh, hold on, still loading. Oh, yeah. Why do you have the fermion determinant getting squared?
Because when I write d slash in this line, what I really mean is the one flavor d slash, whereas here I'm being kind of schematic and there should really be some sum over quark flavors here.
Oh, we're dealing with a two flavor.
Yeah, so we're dealing with a two-flavor theory, and that makes our life easier for making this the square of something.
Just curious, why two flavors specifically?
Because if you want to do things other than two flavors, you should really think a little harder about what you mean by a probability distribution here. And so let's think about that for a minute. And the issue really is that a different color here, we know det d slash plus m squared is real and positive. And I should say we know that det d slash is real from gamma 5 hermiticity. So d slash inverse at x and y is gamma 5 d slash inverse at y and x gamma 5. And so you can track through by multiplying by gamma 5 squared that you get determinants coming out real.
Okay.
But you need a theory with two degenerate flavors to technically have a positive definite determinant that you can do sampling from. So when people include a strange quark where you have one unpaired determinant, then usually what's done is to sample from the absolute value of the determinant. And if the quark mass is heavy enough, then d slash plus m is going to have a positive spectrum, and that single determinant is going to be positive almost always. And so you can simulate with the absolute value and just pay attention to whether your determinant has ever switched sign. And if it does, then really what you should do is include det d slash over the sign of the determinant inside your observables.
Okay.
And formally, you can think of this as you have a theory with a sign. Oh. Looks like I lost screen sharing there. Can you see me again?
Yeah. We can see your fan as well.
Good.
There we go. The screen's working.
Okay. So technically speaking, a three-flavor theory has a sign problem because the determinant is not positive definite. However, for a large enough quark mass, it's a very mild sign problem, and this sign is almost always 1.
Gotcha.
And so you can get away with what's called reweighting, and we'll talk about this more later, where you sample from a different distribution than you wish you had sampled from. So you sample from the magnitude, and then you reweight all your observables by the ratio of what you wish you had sampled to what you actually sampled, and include that in your effective observable. And as long as the distributions are close enough, as long as this thing is close enough to 1 most of the time, you can get away with that without introducing too much noise into the simulation.
Okay. And then just last thing for your particular operator there, you just, randomly are deciding get the VEV of like the, what is that? You said something like the pseudoscalar to pseudoscalar amplitude or something like that?
Yep. And
Okay.
this is
That's just an arbitrary example, right?
and that's an arbitrary example. Though
Okay.
while we're on it, it's an example that's special in one respect. And it's special in that so you've probably seen this worked out, that this is just the trace of the propagator times the propagator dagger. So the norm squared of the matrix that I've drawn here. And that means that the pion correlator sample by sample on any arbitrary background gluon field is a positive definite quantity. That is not true of any other correlation function in lattice QCD. It just happens that the pion is the thing that's written as this norm square of the propagator.
Okay. Yeah, I'd never even heard of that before, so I was wondering if it had something special, but thanks.
Good. So yeah, so this is just a attempt to start an invalid broadcasting session. Not sure what that's about, but hopefully we don't get hit by it too many more times. Okay, so right, and the point of looking at this vacuum to vacuum pion creation, pion annihilation, 2-point function pretty much is that we can compute the pion mass by fitting the large T behavior of it. And similarly, we can compute the whole spectrum of nuclei and the periodic table if we could fit the large T behavior of these nuclear correlation functions without getting swamped in noise and the computational complexity of computing them. But that is a different story. So to talk a little bit about noise, it's useful to have some examples. And the first example that we should always think about is Gaussian noise. And this is going to be stuff you have all seen before, so we're going to move through this and hopefully you don't all fall asleep on the way, but we should be getting to more interesting waters quickly. So let's think about a random variable x, which has a probability distribution proportional to e to the minus x squared over 2 sigma squared. So sigma here is the width of our Gaussian. And we are centered at 0. So the mean we know is 0. A more interesting thing to compute then is the mean square. So to convince ourselves that we can really get this by just plugging in the definitions. Notice that's our definition of the moment, and then we can do any settings worth changing for broadcasting? Has this been something that's been happening before?
No, not really. It's kind of unusual.
Okay, then we will plow on and hope for the best. So we can write x squared as a derivative with respect to minus 1 over 2 sigma squared. And then we can notice that applying that to this e to the minus x squared over 2 sigma squared indeed just brings down a power of x squared, but we can pull this out of the integral over x, reducing our problem of calculating x squared down to the derivative of the problem of the original Gaussian integral, which we will just cite due to Gauss and write this as root 2 pi times 1 over sigma squared. And then we'll see that our derivative will just bring down a factor of minus a half that cancels against the minus a half out here. 2 pi's fly everywhere, and we're left with just sigma squared. Okay, we can do then x to the 4th the exact same way, taking a second derivative of this guy, and we'll bring down 3/2 the second time, so that when the dust settles, we just have a 3 sigma squared. And if you want to get fancy, you can notice that we're just going to bring down powers of 2n minus 1 from every derivative, and so we could really evaluate all of these moments as 2n minus 1 double factorial sigma to the 2n. Okay, but the observation here is that that should be a 4. The observation here is that x could be some dimensionful quantity, and sigma has the same dimensions as x and is the only parameter around with dimensions. So x to the 2n had better be proportional to sigma to the 2n, and indeed it is, and we can work out the proportionality factor as just some combinatorics. So we can then imagine that we were trying to keep screen sharing. If we were handed some data from a Gaussian distribution and trying to answer the problem of estimating the width given the data, then one thing we could do is calculate the average x squared from our data. So calculate x bar squared, which I'll define as the average of xi squared, where xi are our data. And this will give us some estimate that on average equals sigma squared, but has some variance to it. And we can think of well, let's just do the math. So we can calculate the variance on our estimate of the width directly. So the variance is defined to be the average of x bar squared minus the average of x bar squared. And so this is the average of this sum over x squared minus the same thing with the parentheses in different places. Okay, and then we can split up the terms in here into one where we have xi squared, and then, that is very strange. Hopefully it's not too dizzying to switch back and forth with the apps too much. But that might. Okay, so we can split this up into two terms where, good thing there's an eraser around here. In one of the terms, we pick out the products of xi and xi, and in the other term, we pick out the products of xi and xj. And then we also have, it's not right like that, the mean square. Okay, and add back in the brackets. Okay, so now let's look at these. So the first one, this 1 sum over n cancels a 1 over n, and this is just x to the 4th, because we are assuming that our xi are independent, identically distributed with p of x Gaussian, or normal distributed. And again, because these are independent and identically distributed, this is really n times n times n minus 1, good, times, losing squares all over the place, times x squared squared minus x squared squared. And so this guy and this guy cancels out, leaving us with 1 over n x to the 4th minus x squared squared. And it's worth at this point pausing, including the screen sharing, to remark that this is a general result, that the variance average of something, and it doesn't even have to be x bar squared, really just any sum, is 1 over n times the variance of the thing that we're taking the average of. So this is our important lesson number 1. And our important lesson number 2 is, okay, so what did we just say? Our variance of x squared is 1 over n, is x to the 4th minus x squared squared, which is 1 over n. This one we said was 3 sigma to the 4th. This one is sigma to the 4th. So this is really what x? 2 sigma to the 4th. And we can now ask about the signal to noise ratio of our estimator of the width. And this I'll define as the average estimator divided by the root mean square, so the square root of the variance of the estimator. And this we know is sigma squared divided by root 2 over n root sigma to the 4th. Okay, so this is just root n over 2. And there we have it. The signal to noise of our estimate for the width of a Gaussian is proportional to root n and independent of the width. Okay, and so that is how signal to noise should work for anything that is Gaussian or close to Gaussian. So what I want to do now is to go back to Lattice QCD, where we now have learned one important thing, which is that if we define some sample estimate of our correlators, which is the average of our, I'll call the correlation in a given background gauge field C, such that our expectation value of our average correlation function is the true correlation function G. Then, the variance of our estimated correlation function is going to be 1 over n times the variance of the underlying correlation function C. So Lattice QCD, we're always winning by root n. So this is these 1 over root n errors that I mentioned before. The other thing that we can learn in total generality was first understood back in the mid-80s by Parisi and Lepage. And one of the best references for this is a set of summer school lectures actually given by Lepage at TASI in 1989. And Parisi-Lepage analysis can really be summed up as take the variance seriously as a QFT correlation function. Okay. So the point here is that variance of C we can really think of as some expectation of C minus the expectation of C squared. And this expectation value of c squared really is a path integral that we could compute however we're computing our path integrals of c. We compute this path integral of c squared. And this means that this c squared has some spectral representation in terms of a sum over sum of exponentials, just like c did. Provided we can interpret this path integral as a quantum field theory in the appropriate sense. So if we think about a pion correlation function, then the variance of our pion correlation function. Let me schematically draw, I need more colors here. Let me draw my pion correlation function as a pair of quark lines, one going, so time, as always in quantum mechanics, runs from right to left in any quark line diagram I'll draw. So this is a source at t equals 0 for a quark and an anti-quark that propagate in time for some period from 0 to t before they're annihilated. And okay, the correlator then looks like the expectation value of this guy, which we're saying decays by definition like e to the minus m pi t at large times. So now our pion correlator squared will really just look like, well, two of these guys. Again, apologies. I'll see if I can figure out what's going on here for tomorrow at least. So two of these guys then looks like a correlation function that should decay at some energy that is equal to twice the pion mass plus some corrections due to interactions between the two pions. So for simplicity, we'll neglect these and just schematically write this as goes like e to the minus 2 m pi t. But you can actually take this fully seriously and notice that this plus dot 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 here is related to the interactions between the two pions. And you can work out a relationship between the noise in pion correlation functions and the pion-pion scattering length. So it really is that physics giving rise to what's going on in this noise correlator. Okay. But one thing that I glossed over here is that we should be thinking about momentum projection.
Could I interrupt you really quick?
Please.
It isn't immediately obvious to me how the C pi is represented by a loop. Could you explain that again?
Yes, thank you. So what I mean is that this line is representing the Quark Propagator d slash plus m inverse in a given background gauge field. And an arrow going the other direction. So this is really from x to y, and a loop. This, you can also write this as okay. So these two loops then, what I mean is 1 over d slash plus m times gamma 5. Have you seen this gamma 5 hermiticity trick?
No.
Okay, so an unfortunate fact about the Dirac operator is that it's not Hermitian, and we like dealing with Hermitian matrices in physics. So if we remember what the Dirac operator is, it really has stuff that looks like, for Wilson fermions, we have these hopping terms and then some mass terms. And sweeping lots of things under the rug. So is this a form that people have written down here for anything?
I don't think so.
Okay, then I am not going to be able to prove gamma 5 hermiticity in 30 seconds. So let me assert, and you can prove for homework, that d slash gamma 5 is Hermitian, even though d slash is not. And furthermore, that d slash inverse, well, that's only true for the diagonals, so that's really not the important part. The important part is that d slash inverse at x and y is gamma 5 d slash inverse yx gamma 5. Okay, but in trying to put all of the indices into place, we are rapidly getting into the weeds here more than we really need to. So what I want to say really is that pion correlation function looks schematically like a product of a U propagator and a D propagator, with the U moving forward in time, the D moving backwards in time, where these lines just represent Quark propagators, and all of the detailed linear algebra can really be left for another time. So is that enough of an answer to move on for now?
In the double line is because we're in a 2 quark system here.
Yes, exactly. The double line.
That's what was confusing. Again, I'm stuck in a one fermion world.
Very good. So the double line, yes, is that
Okay, gotcha.
the important part is that our pion goes like, let's say UD bar is our pion field, or U gamma,
Perfect.
a U, a gamma 5, and a D bar. And good. So the other thing we can worry about at the level of one pion is what happens to momentum projection. So we can think about a pion at momentum p as something where we just take the discrete Fourier transform over all of the points in the lattice. Of our pion at x and t and our pion at 0. Okay. And what you should notice then is that in general, this pion correlator is complex in a particular background gauge field, simply from having this explicit sum over e to the I px out front. So on average, we should have a sum of exponentials, but the noise for our pion correlation function at non-zero momentum will include fluctuations of complex numbers. So our pion correlation function, we can, again, I'm using C for the individual sample, G for the average. Is really either the real part of the average or the average of the real part. It really doesn't matter. The real commutes through the pathing. However, if we now want to ask about the variance of our sample estimator for G at some non-zero momenta, then it doesn't make sense to talk about the variance of a complex number, or I should say, you have to precisely say what you mean by the variance of a complex number. And so this third expression is one way to precisely say what you mean by the variance of this complex number that has a real expectation value. Is we can just look at the, so without the bar, it's the underlying variance, then this is really real part squared, well, we know the answer, minus g pi squared. Okay, and the real part squared, let's do a little complex analysis. So the real part of z squared is 1/2, well, 1/4 z plus z star squared is 1/4 z squared plus 1/4 z star squared plus 1/2 mod z squared. And so this variance is equal to half the expectation value of mod plus half the expectation value of the complex thing squared minus the expectation value minus g pi squared. Okay, and this magnitude c pi squared is interesting because c pi star of p really looks a lot like c of minus p. So by looks a lot like, I mean they're going to be different on particular random gauge fields, but they have the same quantum numbers. They're the same on average. And in particular, c pi at p and t squared is going to look like this sum for IP x minus y. Okay, and this is a system of two pions with some relative momentum, but no center of mass momentum. And so in the large Euclidean time limit, this is going to look like the energy of the p equals 0 pi system times t, which we'll call roughly e to the minus 2m pi times t. So this means then that the variance of our pion Green's function, which we said had a term that was proportional to this magnitude squared of c pi, is really going to scale like e to the minus 2m pi t regardless of the momentum. So the variance of our sample estimate is just going to be 1 over n times that. And the signal to noise of our sample estimate.
So I have an idea that might fix the thing. Maybe try
Oh,
closing
please.
maybe try closing the other apps. I just noticed above your name in WebEx it had a caution sign saying it might be a RAM or CPU limiting problem. So it's just an idea. I don't know if your
Great.
iPad has a bunch of other apps open. Or maybe it's on like battery saving. I noticed it's charging. I don't know. Worth a shot though.
Worth a shot. There were a couple open. Okay. Are you with me now?
Yep.
Great. Okay. So our signal to noise then looks like.
Oh, we can't see the screen.
Yeah. And
Got it.
okay. So we said our signal in this case should look like the pion with momentum p, but our noise looks like taking the square root of this e to the minus m pi t. And so sticking in the dispersion relation, this is root m pi squared plus p squared minus m pi. Well, it was worth a shot.
Rats.
Minus m pi times t. Okay, and here we are. So if we posit this formula, what we see is that when we set p equals to 0, we have m pi minus m pi is 0 up in the exponent. However, if we have p not equal to 0, then we have a problem. And in particular, if you take p really large, then this will just look like e to the minus pt. So your signal to noise ratio improves like root n with increased statistics, but degrades like e to the minus p with increased momentum. So p goes to infinity limit is exponentially hard, or has an exponential signal to noise problem, is what we'll say. Okay, and that swiping seems to make it particularly unhappy. So that exponent, this root p squared plus m squared minus m, precisely explains the scale of this exponential signal-to-noise degradation shown on the left effective mass plot here. So are people happy with that?
As happy as can be for a signal to noise issue.
Very good.
Or bad signal.
All right, so we can play the game again with the baryon. So a proton correlation function now looks like 3 quarks all headed in the same direction. And our average proton correlation function will scale with the nucleon mass. I'll always be in the isospin limit today. And the nucleon is some particular linear algebra contraction of a product of 3 quark propagators. And it is not in general real in a particular gauge field configuration, just like these non-zero momentum pion correlators. And so that means that when we take the variance of it, we have to use that same formula for the variance of the real part, and we should think about what the mod squared correlator looks like. And the magnitude squared looks like 3 quarks moving forward, 3 quarks moving backwards. Really, again, this complex conjugation looks like time reversal is an important feature that is exactly true in Lattice QCD, but is really what we're using here. And right, so the important part is that we have a correlation function now that looks like 3 quarks going forward in time and 3 quarks going backward in time, or 3 quarks going forward in time and 3 anti-quarks going forward in time. Those are the same quark lines. And no one said that you had to arrange 3 of them into a nucleon and 3 of them into an anti-nucleon. Another state with the same quantum numbers is the different rearrangement of these 3 quark lines, where we pair 3 quarks and 3 anti-quarks. And this suggests then that the magnitude squared of a proton correlation function should not scale with twice the proton mass, but should scale like 3 times the pion mass. And I'm using pion here because it's the lightest state made of 1 quark and 1 anti-quark. So with negative parity, which, if one wants to be technical, and what are summer afternoons for but being technical, we should worry about the quantum numbers. And the quantum numbers of a fermion-anti-fermion pair include negative parity, because anti-fermions have opposite quantum numbers to fermions. So this should really be the ground state system of 3 quarks and 3 anti-quarks that has negative parity. And to get a little more technical, we're including these quark propagators exactly. So the true ground state with negative parity would just be 1 pion. However, the fact that we're putting the quark propagators in by integrating out the fermions exactly, rather than doing things stochastically, means that there's no ensembles where you have fewer quark lines or more quark lines. There's always 6 quark lines. And that you can interpret as another symmetry of the theory of this variance correlation function, that you can't break, you can't annihilate the quark and anti-quark lines from this product separately. And if you take those seriously as the rules for the symmetries of this theory, then 3 pions should be the ground state system with these quantum numbers. And then the signal to noise for an estimate of the nucleon correlation function should look like root n. We have mn as our signal, and now if we take a square root of the noise, then we get 3/2 the pion mass. Okay, and so this is the signal to noise problem of the proton, that you'll have exponential signal to noise degradation at a rate set by the difference between the nucleon mass and 3/2 the pion mass. And because the pion is light and a pseudo Goldstone boson in nature, then this difference is a significant fraction of the proton mass, right? The pion is order 140 MeV, 3/2 the pion mass is 210 MeV, the proton mass is 940, and so we're talking about 730 MeV out of the proton mass showing up in this scale here. So this your signal is really degrading at close to the rate that the signal itself is dropping. And then finally, we can think about the signal to noise ratio for a nucleus with A nucleons, and that at the level of these quark line diagrams is as simple as taking this to the 8th power, which takes this to the 8th power, which takes these 3 pions to the 8th power. And so neglecting all of the interaction effects, which are important and actually give you nuclear binding and all of that, but just to get a sense of the noise scales here, roughly the signal to noise is now going to degrade as A, the mass number of the nucleus, times this mn minus 3/2 m pi scale times the Euclidean distance. And this is the exponential signal to noise degradation, both in time and in baryon number, that we can see visibly in this second plot here on the right. Okay, so that is Parisi-Lepage analysis for pions moving at non-zero momentum, and for protons and for nuclei, and hopefully you get the gist that this can really be done for any correlation function. And okay, sometimes there's some song and dance that I hand waved a little quickly about not being able to break quark lines, but if you accept the rules, then there's a set of well-defined rules for working out what the scalings of all of these signal to noise ratios for any hadronic correlator you can look at are. So any questions before we move on from here? Okay. Then the next thing that I would like to look at is another toy model for noise, because these signal to noise problems aren't things that look like our friendly Gaussian distribution. We saw that regardless of the width of our Gaussian, we always just needed root n statistics to achieve some fixed signal to noise on our estimates. So requiring exponentially large statistics is something different. And for a toy model of that, I would like to discuss a Gaussian Layout. So the setting of the toy problem is that you have a friend with a lighthouse. And the lighthouse mostly works, but it's a little bit noisy. And okay, I'm not much of an artist here, but it should stand on a couple legs and it should have some water, and then, well, it should have some light that it beams out. And you are an observer standing here on the shoreline. And your friend on the lighthouse is going to attempt to send pulses of light timed exactly once a revolution aimed right at you. And most of them will get, well, let me say this is you. And most of the pulses will get close, but they will have some scatter to them. And your friend with the noisy lighthouse has some Gaussian error on when exactly they fire off the pulses. And so as you build a histogram of the locations of the pulses hitting on the shore, then you can, instead of just thinking about the locations of the pulses, if you know that your friend is some fixed distance r away, then you know that you're just looking at some simple trigonometry to relate your random pulses to the angles between which the pulses were meant to be shot out and the pulses were actually shot out. And then you can look at histograms of these angles, where if I could draw a better Gaussian, they would again look like a Gaussian, with the caveat that you're restricted to living between minus pi and pi because this is an angle. And okay, it's a really big Gaussian. Okay, so for a narrow Gaussian, that's not much of a caveat. But for a broader Gaussian that starts to touch the walls with appreciable probability support, then that starts to look like something different than a Gaussian distribution. And in the limit of a totally noisy lighthouse where your friend is just firing off the pulses completely at uniform random, well, then that is also a histogram that we could draw here. And as the Gaussian noise that they're emitting the pulses with gets broader and broader, then this distribution is going to look less and less like a Gaussian and more like a uniform distribution. So to understand what that distribution of random angles should look like, we can go back to our Gaussian distribution and look at the characteristic function, so-called. So the characteristic function is just defined to be the Fourier transform of the probability distribution. In other words, the expected value of e to the I kx, which is really, the integral dx of e to the I kx of the probability of x. So the probability transform of the Fourier transform of the probability distribution. And for a Gaussian distribution, the Fourier transform of a Gaussian is a Gaussian. And so we have a Gaussian characteristic function. And to get from the first line to the second line, we really use the Fourier transform for a real valued variable x that lives on the whole real line, where we could integrate from minus infinity to infinity here. So to think about a Gaussian random angle, we can start with the same characteristic function in Fourier space, and then take a different Fourier transform suitable for a variable that lives on the circle. And let me give it a different name. Let me call it theta. So let's define our probability distribution for a random Gaussian angle theta to be a discrete Fourier transform of the characteristic function. So the probability distribution of x would be the same formula with the sum replaced by an integer, but for a compact variable, then we really just want to sum over all of the 2 pi periodic frequencies. And we can evaluate this by sticking in the representation that I just said. We can say that the characteristic function is the inverse Fourier transform of the Gaussian one. Okay, and then let's just go ahead and plug it in. Okay, and now what we can do is rearrange this equation. So let's get the constants out of here. Let's get the sum inside. All right, I see we should be back. So I just want to exchange the order of summation and integration here. Okay. And now what we can notice is that this sum here is really a sum over Dirac delta functions. So the sum over, oh, and typo. This x has really got to be a theta for this formula to make any sense. That's the theta. Okay. And so, and that is not 2 pi. And this is the danger of doing derivations on the fly. No, I want to do the integral first. No, I want to do the sum first. Okay. Yeah. This is our sum where 2 pi, yeah, x needs to be, the way this should work out is as a delta function in so this should be e to the I k theta, when we have a domain of 2 pi, there's no extra 2 pi there. And so this is ik theta. So then this just says that theta has to be x up to some 2 pi integer. We can then stick that in and now evaluate the x integral using our new delta function. We just have this sum out front. And once WebX comes back, we will see that this probability distribution is nothing other than a sum over Gaussians, where we have our original Gaussian and then we've restored periodicity in 2 pi by summing over all additional 2 pi periodic shifts of the original distribution. So this distribution has a name. It is called the wrapped normal distribution in the field of circular statistics. It turns out that random angles besides lighthouses also show up a lot in geophysics and elsewhere, and people thinking about bird migration patterns and stuff 50 years ago worked out all of the math for these probability distributions of random angles. And they play a little bit differently. So one thing that you should notice is that this is a bad definition of an average angle. And to convince you of this, just picture a probability distribution that is peaked around pi, which is also identified with minus pi. Then this sum over the sample mean of the angles would be something close to 0 on the opposite side of the unit circle as the bulk of the probability. So instead, it makes sense to look at trigonometric functions that automatically have 2 pi periodicity built in. So things like the average cosine is a perfectly nice quantity. And we can compute everything about it in this distribution now. So the average cosine theta is, we know, half e to the I theta plus half e to the minus I theta. And e to the I theta is this characteristic function we were just talking about at 1. This is the same thing at -1. And so remembering it's this e to the k squared sigma squared over 2. Then this gives us e to the minus sigma squared over 2. And so in particular, if our friend is shooting us these lighthouse pulses, if we calculate then the average cosine theta, then we can get sigma squared as minus twice the log of the average cosine. And we can get an estimator for it by looking at this cosine bar that I just talked about. And okay, to think about that cosine bar, we're going to need to look at expectation values of cosine squared so that we can think about the variance. And so this is going to be a quarter 2i theta, a quarter minus 2i theta, and a half times just 1, just a half. So this works out to 1/2 plus 1/2 times e to the minus 4 sigma squared over 2 is 2 sigma squared. Okay, and that's enough then to get to our punchline for the Gaussian lighthouse, which is that our variance for cosine theta bar which remember is 1 over n times this expectation value of cosine squared times the expectation value of cosine all squared, is, we have a 1 over 2n and then one plus e to the minus 2 sigma squared, and then the mean minus 2 e to the minus mean squared sigma squared. Okay, and then we can look at our signal to noise and see, okay, which cos theta over root mean square, and come on, WebEx. We have this 2n out front. We have a mean was e to the minus sigma squared over 2, and then we have this square root of 1 plus stuff in the denominator. And that's really the interesting part, because we can look at two limits of this. So if sigma is small, sigma is near 0, then the signal to noise, we can expand all of the exponentials as 1 plus stuff. And okay, the denominator vanishes at order 1, shows up at order sigma. So this comes out to 2n over sigma, which goes to infinity as sigma goes to 0. Or in the other limit, that sigma goes to infinity, then the signal to noise, the denominator just looks like 1. And so the signal to noise looks like e to the minus sigma squared times root n. And here we have a toy model of something that looks very different from our original Gaussian in this sigma goes to infinity limit. So here we have a signal to noise ratio for estimating the width of our Gaussian that is exponentially small as the width gets large, rather than independent of the width. Is everyone happy with the math there? Well, sounds like as happy as we can be with math at pushing closer and closer to 5:30. So let me give you then the punchline in the last 5 minutes that we can take away from this. So this is a toy model where we get some exponential scale showing up in a signal to noise problem. But what does that have to do with anything? And the answer is that in general, we can suppose that we have some average phase factor that looks like a Euclidean correlation function. And if this is the case, then the variance of an estimate of cosine of the average real part is going to look like 1 over n times half magnitude squared, which is just 1 plus other stuff. And so is order 1 over n times a constant. So that means that the signal to noise ratio of this phase that looks like a correlator is going to look like the average e to the I theta over root n, which is going to be exponentially small in however much mass this average phase contributes to the correlation function. And this brings me to the second way that you can look at decomposing noise in lattice calculations. So instead of just looking at the variance correlator full stop, like in this Parisi-Lepage analysis, we can split things up into looking at the magnitude and phase of a correlator separately. So for the nucleon, we can look at, ooh, don't want geometric shapes there. For the nucleon, we can look at an effective mass that comes from looking at the average magnitude of the correlator. So we take away these phase factors. And if you just take absolute values of your proton correlators sample by sample before computing this expected value and effective mass, then you will get a beautiful effective mass plot that has no signal to noise problem whatsoever, but also plateaus at a scale that has nothing to do with the nucleon mass, and instead empirically lands right about bang on 3/2 m pi. On the other hand, we can look at what happens if we just look at the phase factor, e to the I arg of the correlator, and take expectation values of that and then run them through the effective mass formula. And what comes out is that this average phase factor has a horrendous signal to noise problem at the same severity as the full correlator. And in fact, the effective mass comes out to just about mn minus 3/2 m pi, such that an uncorrelated sum of the phase and magnitude effective mass basically reproduces the full nucleon mass. And so what this means is that this average phase factor is scaling roughly like e to the minus mn minus 3/2 m pi t, and this noise coming from the phase factor is accounting for all of the noise, which we've calculated independently with the Parisi-Lepage arguments earlier and got this same number of mn minus 3/2 m pi. So the last comment that I will make about this, and then take whatever questions we've got, is that this average phase factor is also interesting because if we think about the path integral, then really we're trying to compute an average of an integrand that has some complex phase. So a not positive definite integrand with a sign problem. And what we're learning here is that as we look towards larger Euclidean time or larger baryon number, then the phase fluctuations that give this a sign problem, that make this some gauge field dependent phase factor, are increasing in severity, and our statistical precision of the average real parts of complex numbers with those phases are decreasing exponentially, just like the average noise from this random lighthouse. So that is the picture that I wanted to paint for you today. Any questions?
Great, great. Thank you for the awesome talk. Say, you did a good job. No, I originally did encounter the sign problem in Lattice QCD. I saw it in condensed matter when my undergrad advisor was doing quantum spin liquids, and it was a problem there too.
Very cool. And that's one of the things that I'll hopefully talk about a little more tomorrow, is that, you know, the the noise problems that we see in baryons, the sign problems that finite density people see in QCD, the sign problems that you see in the Hubbard model, these are all the same problem.
Awesome. Well, thank you so much. Yeah. Alrighty then. We'll see if any.
A lot about some of the complications that arise in lattice QCD specifically. But we also talked about a lot of issues that are more general features of quantum Monte Carlo calculations. Sign problems and exponentially hard signal-to-noise problems. And today I want to separate those a little further and dig into a pretty much solvable model where we'll really be able to get our hands dirty and look analytically at what the numerical Monte Carlo noise is really representing quantum mechanics. So to take a few steps back, in relativistic field theories, this doesn't seem to be writing. That's a new one. Huh. Well, let me talk as I debug here. In relativistic field theories, fermions only interact by exchanging bosons. And so we know that in general, we can write our fermion action in a background gauge field in terms of free fermions looking in some gauge field. And really a pen is going to be essential here. Okay, or we can do that. Okay, my handwriting's going to be a little worse today, but we can make it work. So what I was getting at is that for relativistic fermions, we can always write the e to the minus action that lives inside of the path integral as the determinant of a large matrix. And most of the computational cost of lattice QCD comes from the largeness of this matrix. So this d slash is something that in general looks like a derivative. And on the lattice, we write these derivatives as just finite differences. So the derivative as a matrix is really just some collection of ones and minus ones around the diagonal of some large sparse matrix. And in general, d slash is going to be a not quite so sparse, but sparse matrix, sort of like this derivative matrix. And the problem is that when you have 100 lattice sites in 4 directions, then you're talking about 10 to the 8 by 10 to the 8 matrices. You can't take determinants exactly, and you need to introduce algorithms like hybrid Monte Carlo to deal with the quark determinant. So today I want to look at a simpler system where we don't have to deal with those complications right off the bat. And think about, there we are, static fermions. And a static fermion I'll define as having an action that is just psi dagger times x dt psi, or working on a 4-dimensional Euclidean space, I'll just write it as d4 psi, but this is really just the derivative in the 4th direction. And in our lattice theory, this is just a finite difference. And the reason that these are called static fermions is that if we look at the Euler-Lagrange equations that follow from this action, then there's no derivatives with psi dagger, so we can just say that the derivative with respect to psi dagger itself is 0. And so 0 is d4 psi x, or psi of x plus 4 hat minus psi of x. So that means that psi at some displacement t in the forward direction is equal to psi at the same point in space at an earlier time. So these really are static fermions in the sense that time evolution is trivial. Whatever the field looks like at one time, it has to look like at all future times. We happy with static fermions? If this notation looks terribly unfamiliar, please let me know and we can spend a minute on it because we're going to keep using it from here. But if people are happy, we'll move on and turn on some interactions and think about static quarks. And the action for static quarks superficially just comes from capitalizing the d in the derivative, and slightly less superficially comes from saying that instead of just taking a finite difference, we're going to take our field at the displaced time and act on it with some additional field u. And for the case of QCD, u4 of x is an SU3 matrix that represents the gluon field in some way. But you can also think about other choices, and you can think about QED and static electrons by choosing these U's to live in U1. And so that means that the U is just a single complex phase in that case. So that's U mu of x equals some e to the I a mu of x. And that a mu in this picture is the usual photon field that you're used to working with in E&M, the vector potential. And we can repeat the same game that we just did for the static quark and look at the classical equations of motion for quark in a background gauge field and get that 0 is u4 of x psi of x plus 4 hat minus psi of x. And we can solve this, and the unitarity of both SU3 and U1 means that U dagger is U inverse. So we can get that psi x plus 4 hat is just U4 dagger acting on psi of x. And we can iterate this and say that we can get some finite displacement in time by just taking a product of these U4 dagger links on psi. Okay, and that solves the classical theory of static quarks for us and lets us go calculating. So the first thing we can go calculate is the Quark Propagator. So these arrows that we were schematically seeing around yesterday. We can make a little schematic here and say this is the expectation value of a quark annihilation operator. Let's make things easier and just put our source at the origin and say we create a quark at the origin out of the vacuum. We let it evolve for some imaginary time t, and then we annihilate. And we'd like to ask this question in the presence of a particular background gauge field U that we can imagine we'll do some Monte Carlo sample over in real QCD. So we can go ahead then and deal with time evolution. To get this back to 0, and the U here that you should think of as an operator inside the bracket really just acts by giving back the value of the gauge field in that particular configuration. And so we can take that outside, and this is now just psi dagger psi at the same point, which we can stick in an anti-commutator if we want, and that's just 1. So our Quark Propagator is literally just this product of SU3 matrices for the gluon, or U1 phase factors for the photon, which basically just means you add up the photon field in the exponent. In the U1 case, this is the same thing as that, which really just looks like some phase factor from integrating the photon field along the path that you're moving. But for gluons, things are a little more complicated because these U's are in general different matrices at different time slices that don't commute. But that gives us the propagator, and then we can go on, and after mastering one static quark, the next thing to do, of course, is to look at 2. And so we can imagine a system where, let's give this some color, we create now a quark anti-quark pair. So let's say we create a quark at 0, 0, and an anti-quark separated some distance x away, also at 0. And then we let them propagate in time, and then annihilate them with some psi dagger at x and t, psi at x and 0. So what we'd like to ask is, what is the value of this as a matrix element? And so writing everything out in gory detail, we have, I'll say this is x, I'll put in the 1 direction, t I'll keep calling the 4 direction. And so this is our psi dagger psi correlation function. Static quark. Well, this is the static quark pair correlation function. And so perhaps unsurprisingly, if we reverse the direction of this arrow and look at psi dagger at t psi, then we are going to get exactly the complex conjugate of what we got before, which was missing a dagger. So, looking at the equations of motion, it's psi that should evolve with dagger, and psi dagger that should evolve with u. And the other fact that we'll need is that these arrows we have in the t direction, but the same thing holds true in the space directions here, that we're going to need another pair of lines actually connecting our fields here. And the way we can think about this is that we like to get ourselves back from connecting x to 0 just the same way that we evolved in time. So if we want to treat space and time on the same footing here, or if you'd like, if we want to enforce gauge invariance, for those who those are familiar words, then what we should really do is stick in here an extra set of u's along the space direction. So we'll put in some product of u1s at t and another product at t equals 0. And then once we move the fermions back, then we can get everything back to t equals 0 by putting in the same product of gauge lengths that we had before. So now we're just going to have a product of these 4 different sets of u's. And good. This comes out then as really just a product of all of the u's and u daggers around this closed path. And we'll call this a loop, a Wilson loop, named after the person who first started thinking about these in the very first paper on lattice field theory. And this is a Wilson loop of area x times t. And as usual, the reason that these things are interesting to calculate is that there's some other representation that we know something about. So we have psi dagger psi separated by some time t, we can, as usual, insert some complete set of states. And, well, let's cut to the chase, insert also some Hamiltonian time evolution to bring us back to t equals 0. And this will be the usual sum over exponentials times some constant, which we'll just call z. And the energy in this case, we'll notice is a function of the x distance here. And so it's traditionally, well, let's put it this way. We have an En of x times some Zn of x. And we can interpret E0x is the ground state energy for a quark anti-quark pair separated by x. And so in electromagnetism, we know what this is. This E naught of x should just look like the 1 over x Coulomb potential plus, artifacts from the lattice theory that should vanish in the continuum limit. So if everything is under control, then you should be able to calculate the average of this Wilson loop. And extract the static quark potential, I'll sometimes call V, as E of x, which is the limit that t gets big of minus the derivative of log of the Wilson loop. So this is reminiscent of the effective masses that you've been seeing all week. And this static quark potential you can really interpret as the start of a theory of non-relativistic quantum mechanics of static quarks. Because we can do the same thing for gluons as well as photons. And the only thing that's different is the answer, that in QCD, this static quark potential looks like a piece that's coulombic at short distances plus some other piece, let's call it sigma, that grows proportional to the distance. And let's go ahead and call x x. So at short distances, the potential between static quarks looks like the QED potential, but at long distances, it looks very different. And you see this linear growth in the potential corresponds to a force that is constant. And the usual story here is that it takes, if you want to separate a pair of quarks an infinite distance, it takes an infinite energy. So a static quark anti-quark pair is confined. There's no way to separate them with finite energy. And this really just means that the large X limit of this effective mass should be some constant that we identify as this confining potential, and this guy gets a name, which is the string tension, because this potential is the same linear force that you would get from some string theory, and that was a lot of the early motivation for thinking about string theories as effective theories of QCD. But of course, that story played out in a very different history that is a different story that we will not veer into today. So what we want to take away from this, though, is that we can calculate these properties of confinement in a fully complicated gauge theory like QCD by just taking expectation values of these Wilson loops, which are just products of 3x3 matrices around some closed curve. So the most basic questions about gauge theory can be answered at a first pass without having to include this quark determinant that makes things much more expensive. And so this is what was originally done back in the 80s and 90s, was people simulated these theories of just gluons and then asked questions about static quarks and background gluon fields, or eventually dynamical quarks and background gluon fields. And you can learn interesting things that way. So what I'd like to spend the rest of the day on then is an even simpler version of this pure gauge theory, where instead of SU3 gauge theory of gluons, we're just going to look at U1 gauge theory. So this is QED, like I said. And I see the question from Ben, is that form of Vx a guess, or was there a reason that was chosen? So this Vx is it's a good guess, or a phenomenological model. But the 1 over x you can work out has to be there in perturbation theory. And while I won't go into it in detail, one of the most critical properties of the strong interaction is that it gets strong at strong distances, but is weak at short distances. And so the short distance form of the static quark potential can be calculated in QCD perturbation theory and has this 1 over x form. So that's sort of known. This plus sigma x is a general prediction of phenomenological models. You can look at things from the opposite direction of strong coupling, though that expansion is a little more complicated as to how to get away from infinitely strong coupling with it. But suffice to say, this linear term is a guess that appears in a lot of phenomenological models of quarks. And what you calculate in Lattice QCD would be, the values of the effective mass as a function of area. You would get something similar to these effective mass plots that we had the other day, where you'll just have some points with error bars from the Coulomb part, and then flatten out into some linear rising part. And what I'm drawing here, unsurprisingly, is that the errors are going to end up being exponentially large in the separations in either space or time. So because the lattice data is in any calculation going to be noisy points, it's helpful to have some phenomenological parameterizations that you can fit to your data at the end of the day in order to have some useful form to deal with. Anything else on the static quark potential in general before moving on? Okay, so what I want to talk about for the rest of our time today is U1 gauge theory in two space-time dimensions. And Euclidean space, so that's really just two space dimensions. And we talked about these Wilson loops. So in U1 gauge theory, our U mu of x, we said, is just e to the I a mu of x. It's some U1 phase at every lattice site in both the directions. And the smallest Wilson loop that we can build is a 1x1 loop, which we'll call a plaquette. So just to write it out in more detail once, the plaquette is the product of this pair of U's and U daggers forming a loop here. If you imagine, again, like the Quark Propagator, is that your U, this is the mu direction, and this would be U mu of x, is what I mean by that line. And the plaquette plays a bit of a special role because it so any of these Wilson loops where we draw a closed shape are also gauge invariant objects. And the Wilson loop is the trace of the plaquette is the simplest gauge invariant object. And it turns out that one over g squared times the real trace of the plaquette is a very good guess for the action. And it's a good guess in some sense because it's the simplest gauge invariant thing you could guess. But the important point is that this, if you expand out U mu as a Taylor series, so if you say U mu of x is approximately 1 plus I a mu of x, then what you'll work out is that this action is equal to the usual Maxwell action for electrodynamics. So what that means is that this plaquette action has the right naive continuum limit. And so one hopes then that if you simulate at a range of lattice spacings and then take the continuum limit at the end, that you will reproduce the physics of electrodynamics. So that basically defines the theory. The partition function, the only other thing we need to know is what's the measure. And okay, we're integrating basically over e to the I angle, so perhaps unsurprisingly, the right choice of measure is just dA over 2 pi. And so this is our partition function for the theory. But in 2 dimensions, there is a pretty snazzy thing that happens, which is that there is only, there's only one of these plaquettes because there's only one space and one time direction. So there's only one plane for the plaquettes to be oriented in 2 dimensions. So I'll just start calling it P, and we can write P as e to the I well, we know where it's going. Okay, the other snazzy thing about working in 2 dimensions is that most of these links don't actually matter. And if we imagine setting all of the links that I just highlighted to 1, then we still have 4 leftover links, and we still have 4 of these plaquettes. And you can show that you can actually, that the action only depends on these 4 link variables that I haven't highlighted and is independent of the rest of them. So we can trivially do the integrals over all of the blue highlighted links and just get 2 pi, since these integrals are all from minus pi to pi. And if we define our plaquette to be some e to the I theta, which theta will be some linear combination of the a mu's like so, then our partition function just becomes a product of integrals over these thetas, and the action that I forgot a minus sign on here, real trace is just the real part of p of x, and this should be summed over x, and this just becomes a product of one-dimensional integrals. So we don't even need to call it theta of x anymore. It's just some integration variable theta, and the real part of the plaquette is just the cosine of theta. And so this is just some integral raised to the power v, where v is the number of plaquettes on the lattice. And this integral has a name, so there's a set of special functions called the modified Bessel functions that you may or may not have seen before. So the nth modified Bessel function is defined as this Fourier transform like integral over an e to the cos theta distribution. And so z is then the I0 Bessel function of 1 over g squared to the vth power. Okay, that's a mouthful, but it's a known analytic answer of a function that's tabulated and well known in Mathematica and wherever you go for special functions. And we can not only calculate the partition function, but we can also look at Wilson loops. So a Wilson loop, we know, is this product over all of the links in the boundary of a big square. And you can get the same thing by putting in all of the little links inside and going around a much longer path where, but we should probably get the arrows consistent. But we can take a product of all of these 4 plaquettes and get out the same thing. So the product over, I'll say if this is the Wilson loop of area A, then we want to take the product over all the links in the boundary of A, but this is the same thing as taking the product of these plaquettes over all of the points in A. And this means that we can take expectation values using this exact same factorization that we had before. So we have some product over all of the plaquettes in the lattice, and this P of A I'll write as, again, e to the I theta.
Can I ask, is the fact that the interior legs cancel out specific to U1 or like an abelian group?
Yes,
Okay.
it is. So yes, that is specific to U1. For SUN, you can take a slightly more complicated construction where instead of P of X in this, you basically replace P of X with products of extra matrices to transport each plaquette back to a common point.
Okay, that's good
But
enough. I don't need to delve into that. I was just wanted to make sure I wasn't being overly constrained and thinking that it would only work for that. But okay, so it only works for U1. Thanks.
yep, so to keep things simple, it only works at face value for U1. And okay, so what we'll get then is everywhere inside of the Wilson loop, we'll have to do this integral with an extra e to the I theta. And everywhere outside of the Wilson loop, we'll have the integral that we had before. And importantly, there should be a 1 over z out front. And okay, this integral has the name Bessel I1. So we have Bessel I1 of 1 over g squared to the a, and then everywhere outside of the loop, we just have this Bessel 0, and then we also have a big product of v Bessel zeros from dividing by the partition function. And so most of these are going to cancel out, and so we have I1 of 1 over g squared over I0 of 1 over g squared to the 8th power. And we can notice that we can rewrite this as e to the minus sigma a, where sigma is the log of Bessel 0, 1 over g squared over Bessel 1 of 1 over g squared, and the one fact that I will appeal to about these Bessel functions is that Bessel 0 is bigger than Bessel 1 is bigger than Bessel 2, and so sigma is greater than 0. And so what we have therefore proven is that the string tension, the limit as a goes to infinity, we can just write it as a minus dA log of the Wilson loop, is precisely this sigma, and it is some number greater than 0. And thus we have proven that QED confines static electrons in 2D. Okay, and that in 2D turns out to be crucial. If we try to do this in 4 dimensions, then the fact that there are multiple different planes that you could tile your plaquettes in means that the action doesn't factorize nicely into this product of independent integrals over each plaquette. And this derivation breaks down from the get-go. And instead, you need to go ahead and compute the Wilson loop numerically. And what's found is that in 4D, for large G, you see confining behavior. And then for small g, you see a transition to Coulomb-like behavior, where electrodynamics, as we know and love, allowing free electrons to get off to infinity with finite energy, it re-emerges in the continuum limit. But here it is crucial that we get to the continuum limit. So what is meant by confines is this property that we were talking about back when we were talking about static quarks, that V of infinity is infinity. It takes an infinite amount of energy to separate a static quark-antiquark pair. So this says that in 2 dimensions, it would similarly, well, here our potential, so let me write here our Wilson loop, which we expect to be some sum over energies times time, as really just a single term. And so the static electron potential, which is the ground state energy here, is equal to sigma x for all t. And so we just have this linear confining part. So the integral does not factorize in 4D. In general, it factorizes at strong coupling, but away from the strong coupling limit, it doesn't factorize. And that's really why we need the sort of computer architectures that we do to do lattice QCD, is the action couples nearest neighbor links. And so you need this communication between your lattice sites to update the field because of this lack of factorization.
Might I ask quickly, in your expectation value of WA about halfway down the page, so the first product in your integral is the things on the loop. That's the U functions on the specific path you're going to use, right?
Yeah,
Now,
so
the second one was what I was going to ask about. The second one, you have product of X not in A.
yeah,
I think you might have gone over that on the last slide, and it didn't settle in.
right. So in general, we're trying to take the integral of this Wilson loop times e to the minus action.
Yep. So the e to the minus action is on the right, is the
So
right-hand term.
e to the minus action is this product of e to the cos thetas everywhere.
Okay. Do you have X is not an element of A written there? I might just be.
Yes, sorry, that's X not in A.
Yeah, okay, that's the only thing. Why is it restricted to the points not in A?
Because the points in A are also there. So this is the e to the minus action from the points in A. And
Right.
all I'm saying is that there's an extra factor of e to the I theta.
Oh, I see. I see what you're doing. Okay, yeah, I completely forgot. I was reading off the e to the I theta as e to the cosine theta. I didn't see the second term in there. All right, that's good.
Yeah.
Thanks.
So this is the action term. This is our observable here.
Gotcha. And that's the all important factorization.
Exactly.
Okay.
Exactly. And the factorization is really, really cool. So let me just sort of cut to the chase here, but we can calculate not only the Wilson loop, but also the variance of the Wilson loop. So putting back some formulas from yesterday, our Wilson loop is a complex number. And so the variance of the real part is going to have these two terms that look like the mod squared and the complex number squared. And since the Wilson loop is just this e to the I theta phase factor, this mod squared is just 1. This expectation value of WA squared is something else that looks like e to the minus A with a different sigma there. It's a modified Bessel function number 2 for those keeping score. But we can immediately read off then that we have an exponential signal to noise problem for these sort of Wilson loop calculations. And to convince you that that's true, even in 2 dimensions, here is a plot of the effective mass of a Wilson loop. So we know the exact answer is e to the minus sigma A, where sigma is some number that we can relate analytically to the coupling that we enter into the theory. So the blue points that I'm showing here come from saying, let's fix sigma to be 0.1. Let's calculate what gauge coupling corresponds to sigma equals 0.1 using this formula. And then let's run a Monte Carlo simulation using that coupling, calculate the Wilson loop, calculate the effective mass of the Wilson loop, and make sure that we get back that sigma equals 0.1. And that is indeed what you see here. And then in the bottom curve, there is the signal to noise of the Wilson loop plotted. And the green curve shows that this analytically predicted signal to noise actually reproduces things.
Could you repeat you input G into the simulation like at a fixed value and then you have a predictable value of sigma out?
Yeah, so the simulation, remember, is saying that we want to Monte Carlo integrate, sure, we can even get the normalization factor in here. We want to sample from this probability distribution, and we want to take products of independent phases sampled from that distribution, and we can get our Wilson loops from that. So because of factorization, you don't actually need to simulate a whole 2D lattice of points. You can just simulate this distribution here and then take products of independent things coming from it. But yeah, conceptually, it doesn't really matter. All I'm saying is that we sampled from this distribution where G was chosen such that this messy function of G was equal to 0.1.
Okay, so in any case, you've picked a G beforehand, and you're gonna do your sampling, and then you're gonna extract sigma from the Wilson loop of the that you do the sampling to generate. And
exactly.
Then you hope to recover the correct sigma out. Okay, gotcha.
Okay, and the first punchline is basically that Monte Carlo works, and you do get the correct answer out. And if we had a little more time, I would go into these other points on the plot here, which, suffice to say, come from a trick for attempting to improve these signal-to-noise problems. And if you are interested, you can jump to the paper for more details. But the trick is basically coming from using Cauchy's theorem, which says that any integral of an analytic function is unchanged if you deform the contour of integration. And the magic is that the expectation value of the Wilson loop is an analytic function, but explicitly includes these absolute value bars is not. And therefore, changes of your integration contour can change the variance without changing the signal. And that is all I want to say in 30 seconds about attempts to actually use this perspective to profit. But suffice to say that there is still a lot of ongoing work in the community to take what we can understand about these noise distributions and try and get some leverage to improving the way we can use Monte Carlo sampling by using some of this. And with that, I will take any questions that you all have.
The classic virtual Q&A. You can't tell if anyone's going to type anything.
Indeed. Well, seeing none, I will let you take a well-deserved break from your day of lectures and prepare to do it again tomorrow. So I hope you all learn something and make the best out of this virtual summer school experience. And please, if I'm sad that I don't get to chat with you all in person while you're at the summer school. So if there's any questions about things in these lectures or just other gauge theory, physics questions that you have, please feel free to email me and reach out, and I'd be happy to connect more.
Great. Thank you so much for coming, or well, not coming, but being here, Dr. Wagman.
Absolutely. It's been fun.
Awesome. We've enjoyed it a lot. Thank you so much.
Thanks so much.
All right.